In this video, we will go through the procedures for doing a Spearman rank order correlation. Remember that the Pearson correlation works with data that are measured on continuous scales. But sometimes data are not measured on a continuous scale. They may be in the form of rank orders, or there may be circumstances where data that are measured on a continuous scale are better understood if they're transformed into a rank order. If that's the case, then the Spearman correlation coefficient can be applied and is more appropriate. Remember that the Pearson correlation is designed to work when both variables are measured on a continuous scale. Some data are not measured on continuous scales, though. Some data are in the form of rank orders, like, for example, where you finish in a foot race. Remember that the Pearson correlation coefficient is designed to work when both variables are measured on continuous scales. Sometimes data are not in the form of continuous. Remember that the Pearson coefficient is designed to work when both x and y variables are measured on continuous scales. However, some variables are not measured on continuous scales. They are in the form of rank orders. For example, the positions of finish in a race, first, second, and third, are on an interval scale of measure. They're in the form of ranks. So that's one application where the Spearman correlation coefficient would be appropriate. Other times it might be appropriate to transform measures on a continuous scale into rank orders, and there again the Spearman correlation can be applied appropriately. If two variables are consistently related, that is, if the slope of the regression lines needed to account for the direction of the relationship between x and y don't change radically from a positive slope to a negative slope, then the rank orders of these nonlinear relationships will be linearly related. So that's why it's sometimes good to transform observations on a continuous scale of measure to rank orders. If you look at the top left graphic, you can see an example of poor linear fit. The actual data points are curvilinear, and a Pearson coefficient would just be the fitting of a straight line to the data, and you can see there's quite a lot of error involved in such a procedure. If you look at the graphic next to it, we see a highly curvilinear relationship between x and y. This is a kind of a familiar Yerkes-Dodson curve, which shows that low or high amounts of anxiety are related to poor performance, but moderate amounts of anxiety are related to better performance. It would be impossible to fit a straight line to these data, but more importantly, because the relationship is not consistent, it has both a positive and a negative slope. It would not be possible to describe it linearly using the ranks of x and y. On the other hand, down here at the bottom, we have both a curvilinear and a consistent relationship between x and y. So the ranks here will be linearly related. If you look at it, the slope of the regression line is consistently positive throughout that relationship between x and y. It never does turn negative. So we can go ahead and convert those observations to ranks and correlate them with confidence that we'd be able to detect a linear relationship among the ranks. Here's the Spearman correlation formula, one of several ways to calculate the Spearman coefficient, but at the left here we see the number 1, and from that we're going to subtract this term to the right here, where we take 6 times the sum of the squared difference scores and divide that by n times n squared minus 1. And once we perform all those operations, we will have the Spearman rank order correlation coefficient. Here's an example. Remember that in a Spearman coefficient, n is used to find the critical value of r, not degrees of freedom. Hypotheses are structured, though, exactly the same way for Spearman as we learned in Pearson. So we could have a two-tailed test of the hypothesis as we have here. We can also have one-tailed test of the hypotheses. So here I have two variables, x and y. My sample size n is 8. Whoops. And let's redo that. Here's an example. Remember that for the Spearman coefficient, n is used to find the critical value of r, not degrees of freedom, as is the case with a Pearson coefficient. The hypotheses, though, are structured exactly the same way for Spearman as we learned to do it in Pearson. So we can have one-tailed test of the hypothesis, or we can have two-tailed tests as we have here. So we're going to reject the null hypothesis if the calculated value of r is greater than our critical value, and our critical value from the table is 0.738. We have a separate table for finding the critical values for the Spearman correlation. It's the table exactly behind the table in the back of the book for the Pearson coefficient, table B6. To find the critical value, you need to know n, you need to know. In order to find the critical value for a Spearman coefficient, you go to table B7 in the back of the book. There you'll find the critical values, and remember that for Spearman we have to know n, not degrees of freedom. So n is the index value there. We have rows for one-tail and two-tail tests of hypotheses, and then alpha levels such as 0.05 and 0.01. So in the example that we're pursuing, we're doing a two-tailed test with an alpha level of 0.05, and our sample size is 8. So you would look on the table, and there is the critical value, 0.738. The first thing that we have to do is rank order the observations. So over here we have the x values, and next to that we have the ranking of the x values. I simply started with the highest value and gave that a ranking of 1. The next highest value, which is 14, gets a ranking of 2. The next highest value gets a ranking of 3, and so forth. No problem. We come over here to the y values, though. We do have some differences in how the set of numbers is structured. We have, for example, 2 8s. Okay, now continuing with our example, remember that the first thing we have to do for a Spearman coefficient is we have to convert our observations to ranks. Over here on the x values over here, I'm going to do that, convert them to ranks. I start with the highest observation, which is 15. That gets a ranking of 1. The next highest observation is 14, gets a ranking of 2. The next highest observation is 12, it gets a ranking of 3, and so on. We do the same thing for the y values. So if we look at the highest value in this set of observations, it's 22, and that gets the ranking of 1. The next highest value looks to be the 13, so it gets a ranking of 2. Now, further down, there are some observations that are tied. For example, we have 2 11s and we have 2 8s. We'll deal with the 11s first. So moving on through the list of the numbers here, 12 is the third highest observation, so it gets a rank of 3. So 11s, the 11s would be ranked 4 and 5, and the average of ranks 4 and 5, or 4 plus 5 divided by 2, is 4.5. So we have those ranks there. Each observation, each of the 11s is ranked 4.5. And we do a similar thing for the 2 8s. Those ranks would be 7 and 8, and the average of 7 and 8 is 7.5. 7 plus 8 divided by 2 is 7.5. So that's how we deal with tied observations in a Spearman coefficient model. Once we've rank ordered the observations, we no longer deal with the original observations. So you can see here that I've eliminated them. All that we have left are the rankings. From there, what we do is obtain the difference scores. We just subtract the Y rank from the X rank. In the first case, it gives us a 0. 7 minus 6 gives us a 1. 3 minus 2 gives us a plus 1. Okay, once we have the ranks, we no longer deal with the original data. So I've eliminated that, and you can see that all I have here on the screen are the ranks of X and the ranks of Y. So to proceed, what we first need are the difference scores, and we just get that by subtracting the rank of Y from the rank of X. And in the first case, that value is 0. 7 minus 6 is 1. 3 minus 2 is 1, and so on. Once we get all of the difference scores, then we have to square them. That gives us d squared here, and we have to add them up or get the sum. So the sum of the squared difference scores. In this example, the sum of the squared difference scores is 30. And remember, that's a term that's needed in the numerator of our Spearman coefficient. This slide just walks us through the calculations of for the example of the Spearman coefficient. We have the 1, which is part of the formula, 6, which is part of the formula, times the sum of the squared difference scores, which we saw in the preceding slide, was 30. Down in the denominator, we have n times n squared minus 1. So we work inside the parentheses first. So 8 squared is 64 minus 1 gives us 63. So if you look down here, that's the step I've done here. 8 times 63 is 504. So in the third step, I have 180 divided by 504, which gives me, in the fourth step, 0.357, which I have to subtract from 1, and my resulting Spearman coefficient is 0.64. Well, 0.64 is a good value. It's plenty high enough, but unfortunately, in the context of an example that only has 8 observations, it's not quite high enough to reject the null hypothesis with an alpha level of 0.05 and a two-tailed test. So our calculated value is 0.64, but remember our critical value was 0.738. And because it was a two-tailed test, we would reject the null hypothesis if this calculated value had been greater than plus 0.738, or if it had been less than negative 0.738. But 0.634 is not within the critical region, so we actually failed to reject the null hypothesis in this example.